In this equilibrium lecture, we're going to discuss Le Chatelier's principle. So Le Chatelier's principle deals with what happens when we change the conditions around equilibrium. So let's remind ourselves that at equilibrium, we have two reactions taking place. There's the forward reaction and the reverse reaction. And at equilibrium, all we know is that the speed of the reaction is the same in both directions. But there's no relationship between the speed of the reaction and the value of K. We just know that at equilibrium, they're both happening at the same rate. What K is a relationship between the concentrations of product to reactant at equilibrium. And so in this scenario, we started off with all reactant, ended with a mixture of reactant and product. Now, if we stress the system in some way, change some conditions somehow, either by adding more of a product or reactant or changing the temperature, then we're going to see a change in the rates of our forward and reverse reaction. In other words, if you stress out the system is going to respond. This is in essence what Le Chatelier's principle states. When a stressor is applied to a system at equilibrium, the system will react in such a way as to relieve that stress. So one way of thinking about this is, will our reaction shift toward our reactants or products? So we can abbreviate Le Chatelier's principle as shift happens. So these are the types of stress we are going to examine in this talk. Changing concentration, changing pressure and volume, and changing temperature. These will all affect our equilibrium and mess it up, and then the system will move back toward equilibrium, and the way this happens is dictated by the type of change, and we will see several examples now. So Le Chatelier's principle is really what keeps us alive, which is why it's so important to understand. So a mammalian fetus is in utero in an amniotic fluid-filled sac, and they don't have gills, so they can't breathe underwater, and so fetal hemoglobin has to get oxygen from somewhere. So what happens is, through the placenta, the fetal hemoglobin is brought into close proximity of the adult hemoglobin, and there is gas exchange between the two fluids and waste and food exchange. And the fetal hemoglobin is attracting oxygen much more strongly, and so it can bind oxygen at a lower concentration. So then this fetal hemoglobin can then carry oxygen to the fetus and away from the adult. This is a similar idea to how our blood cells work. So the iron in hemoglobin loosely binds oxygen, and the concentration of oxygen is much higher in the lungs than it is in the muscles. So you could imagine this as a simple equilibrium where you have free hemoglobin, free oxygen, and oxygen bound to hemoglobin. In the lungs, where you have a really high oxygen concentration, we shift to the right. We see more oxygen binding to the hemoglobin. However, when we get to the tissues where there is very little oxygen, then the reaction has to shift to the left, and the hemoglobin releases the oxygen, which is then able to be used by the tissues. So these are some of the types of stress that we are going to examine. So what happens if we change concentrations? What happens if we change the temperature? What happens if we change the pressure or volume? So why don't you take a minute, and if you are able to, stop this video and make some predictions of what you think will happen in each of these scenarios. Identify whether you think the reaction would shift to the right, meaning more product would form, or if you think it would shift to the left, meaning more reactant would form. So let's look at the effect of changing concentration first. In this scenario, we have N2O4 in equilibrium with NO2. If you add more nitrogen dioxide, which in this case is the product, then we see that system shifting to the left. Well, why is that? Well, we've disturbed the equilibrium by increasing the amount of product. So you can think of this as we've changed that reaction quotient. So we're not at equilibrium anymore. So the ratio of product to reactant is now Q. And it's going to be larger than our K value because we have a larger number on top of the denominator. And so in order to go back and get that K value back to where it was at equilibrium, so that Q and K are now equal to each other again, more N2O4 must form. So in this scenario, the actual concentrations of these two will have increased, but the ratio will not. The value of K does not change simply because you've changed the concentration of reactants or products. So you could also imagine a scenario where the nitrogen dioxide is allowed to bubble away, in which case the reaction would be driven to the right. So when we add product or remove reactant, we shift to the left. When we add reactant or remove product, we shift to the right. Now let's consider the effect of changing pressure or volume. So what types of reactions would changing the pressure when would that even affect equilibrium, and when do we need to consider Le Chatelier's principle and pressure? It's when we're dealing with gases. So the ideal gas law shows us how pressure and volume and the number of moles are related. So pressure and volume are inversely proportional, meaning that for a gas with the same number of moles, this is a constant and at the same temperature. So you can imagine you have a container with a piston on it and it's at the same temperature. This is a constant and you have the same gas, so the same number of moles. If you press down on that piston, that decreases the volume, you've increased that pressure. And if you pull up on the piston, increasing the volume, you decrease the pressure. So that's what that means by inversely proportional or inversely related. So decrease volume, increase pressure, increase volume, decrease pressure. Pressure and volume each are proportional to N. So if we increase the number of moles, then we also increase the pressure and volume. So increasing pressure and volume could increase, or increasing moles could increase pressure, volume, and decreasing moles could decrease the pressure. So here's an example of Le Chatelier's principle in action with gases. So we're changing the volume and consequently the pressure of this syringe. So we've got this NO2 gas, which is dark brown, and the N2O4, and it's being held in this syringe, and then we release the piston. And did you see how the gas gets lighter initially? Because N2O4 is colorless, but then it reestablishes its equilibrium and gets dark again, so that we get the same concentration, the same relative concentration of NO2 to N2O4 in our container. So here's another way of looking at this. Here we have a piston, a container with a movable piston, and we can increase the pressure, decrease the volume, or decrease the pressure, increase the volume. A change in pressure or volume does not change the overall K value, but we will see that the reaction will shift toward the side with the fewer moles of gas particles, with an increase in pressure, and we'll see it shift to the left with a total decrease in pressure. And this comes from that relationship between the proportionality of N, the number of moles, and pressure and volume. So in this example, we've got 4 moles of gas on our reactant side and only 2 on our product side. So when we increase the pressure, we shift to the right. When we decrease the pressure, we shift to the left. So in this scenario, where you're increasing pressure or decreasing volume, the reaction is going to shift toward the side with fewer moles of gas particles. Okay, over here we've got 4 and here we've got 2. In order to equilibrate the pressure, we need to have fewer collisions between the sides of the container and the gas particles, and so we have to have fewer gas particles. In this example, decreasing the pressure or increasing the volume causes the reaction to shift to the left toward the side with more moles of gas particles. So when thinking about changes in pressure or volume, you have to be very careful that you don't focus entirely on right versus left. It's not necessarily the product or reactant that tells you the answer. It's the number of moles. So just remember that if you are compressing the gas, you need fewer moles of gas particles. And if you are expanding the gas, you need more. So compression, shift toward fewer. For expansion, shift toward more. Now let's look at changing the temperature. This one is different because changing the temperature will change K. And it's also dependent on whether or not a reaction is exothermic or endothermic to determine the direction of the shift. So in this top reaction, we have ammonium nitrate dissolving in water to yield ammonium and nitrate ions. And then on the bottom reaction, we have calcium chloride dissolving in water to form calcium and chloride ions. Now, if you were to mix these into two different beakers and put your hand on the beaker, this top reaction would feel cold and this bottom reaction would feel hot. Now, this reaction right here is how those instant ice packs work. There's a pouch of ammonium nitrate and there's a little inside of that pouch, there's a smaller pouch of water, and you pop that water, and as soon as it starts dissolving, it gets very cold. So let's think about what exothermic and endothermic mean. Endothermic means we have a positive delta H and energy must be absorbed from the environment. That is this kind of reaction where it feels cold because energy is being pulled in away from the beaker, away from your hand. This reaction is exothermic. Energy is being released into the environment. There's a negative delta H and that energy is leaving the reaction to the beaker, to your hand, and it feels hot. So for an endothermic reaction, we can imagine heat as a reactant, and for an exothermic reaction, we can imagine heat as a product. And so when you're trying to determine the direction of shift for an exothermic or endothermic reaction, you want to look at where heat is. Now, if you know, for example, how the reaction responds to a change in temperature, then you can determine whether or not a reaction is exothermic or endothermic. And let's look at this example here. So we've got nitrogen gas and hydrogen gas forming ammonia. At equilibrium, they are in this ratio, and then we start to cool the mixture, and then equilibrium is eventually reached again. So temperature is going down, and we see that we get an increase in product. So that means that we have heat is a product as well, because cooling the reaction allows more product to form. So we must have an exothermic reaction here. Now notice how the concentrations of our components at equilibrium is different because we've cooled it off than it was when we started. And that is because we have to remember that changing the temperature changes K. So equilibrium constants are only constant at any given temperature. So let's look back at our types of stress and make sure we understand how these types of stress affect a reaction. So in this scenario up here, we can add more A and we will shift to the right because we have too much reactant now, we have to make more product. If we add more of a product, then we're going to shift to the left. We want to break down that product and move toward reactant side. If we remove some product, like if it bubbles away as a gas, then more will need to form, so we will shift to the right. If we increase the temperature for an exothermic reaction, we will shift to the left. And consequently, that means that decreasing the temperature for an exothermic reaction shifts to the right. And then if you increase the temperature of an endothermic reaction, that shifts to the right. And the opposite is also true. So decreasing temperature, it would shift to the left. Increasing pressure means we have to shift towards more moles. Decreasing the pressure would be towards fewer moles. So let's do an example problem. The reaction of sugar with oxygen is exothermic. Let's predict the effect for each of the following scenarios. We increase the temperature, we remove carbon dioxide, or we change the volume. So if we increase the temperature of an exothermic reaction, that means we are adding a product, and so we would expect the reaction to shift to the left. CO2 is a product, and so by removing product, we have to then adjust for that and increase more product concentration. So then we would shift to the right. If we increase the volume, that means we're going to decrease the pressure. So we're going to increase the number of moles and shift to the right. We have more moles on the right side of this equation than we do the left. Here we have 12 moles, and over here we only have 7. If the decomposition of ammonium hydrosulfide is endothermic, which of these will cause the more formation of H2S? So we have solid ammonium hydrosulfide in excess, and it reacts to form ammonia gas and hydrosulfuric acid. So we have a decrease in volume of the reaction vessel, an increase in the amount of this in the reaction vessel, an increase in temperature, or all of the above. So we can right away eliminate B as a correct answer, because increasing the amount of the solid isn't going to affect the equilibrium. It is not part of our equilibrium expression. So we know it's not B, and if we know it's not B, we also know it isn't D. So then let's consider A and C. If it's endothermic, that means that heat is a reactant, and we want to drive the reaction to the right. So if we add more of a reactant, we'll get more of the product. So increasing temperature would in fact drive the reaction to the right and get us more H2S. So let's consider what happens if we decrease the volume. Well, decreasing the volume means that we need to go toward the side with fewer moles, and that would be to the left, and so that's not going to get us more H2S. So we are in fact correct by picking C. Now let's consider these scenarios. Coal, which is mostly carbon, can be converted to natural gas, which is mostly methane, and it has a delta H of formation of negative 74.5 kilojoules per mole. So right away, this tells you something about the reaction. It tells you that it is an exothermic reaction because it's releasing heat. It has a negative delta H of formation. So let's see which disturbances will favor more methane. Well, adding more carbon to the reaction mixture won't affect anything because it's not part of the equilibrium expression. Adding more H2, that's adding a reactant, so that it typically would drive the reaction forward, so B is a good choice. Raising the temperature of the reaction mixture, well, it's exothermic, so heat is a reactant, so if we add more of a reactant, we're probably going to go to the left, so I don't think C is a very good answer. If we decrease the volume, that means increasing the pressure, then we need to go toward the fewer moles side. And we see that there are 2 moles of gas here and only 1 mole here, so D looks like a good choice. And then E, adding an inert gas that's not doing anything with this reaction isn't going to change anything because it's not going to affect the components of the equilibrium expression. So it looks like our 2 answers are B and D.